Well, a random variable is a variable that is associated with the sample space of a certain random experiment, where the random variable would be defined to be studying a certain aspect of this random experiment, or the outcomes of this random experiment. In fact, we can look at it as being a statistical variable that would study a certain category of outcomes of a random variable that would in fact be studying the probability of occurrence of these outcomes or these values, rather than studying the frequency or the number of occurrence of such events. So if we were to make sense of this variable, we could just look at the example we have here. We are tossing two coins simultaneously. Now the sample space of this random experiment would actually be represented by this set omega, which consists of four ordered pairs: head, tails, tails, head, and tails, tails. And you could actually determine this sample space by making a simple tree diagram. So over here for the first coin, we have the possibility to end up with a head or a tail. Then for the second coin, with a head for the first one, we could have either a head or a tail, and with a tail for the second one, we could have either a head or a tail. So over here, we look vertically at the possible outcomes that represents the sample space of this random experiment. So over here, we could end up having two heads, a head then a tail, or a tail then a head, or two tails. So if we introduce a random variable x to the sample space, now on each sample space of each random experiment, there are several random variables we can introduce. So it really depends which aspect of the sample space or the random experiment you wish to study. So if over here we consider the random variable x that represents the number of heads obtained. So over here we are aiming to study how or number of heads that you obtain when you toss these two coins. So whenever you introduce a random variable to a random experiment on its sample space, the first thing you need to do is to give the possible values that this random variable can take. For example, if you're tossing two coins and given this set omega as the set of sample space, so over here, how many possible heads could we end up with? For example, if we look at this outcome could have two heads. If we look at these two outcomes would give me back one head, and this outcome would give me 0 heads. So the possible values that this random variable can take are 0, 1, and 2. So over here, 0, 1, and 2 represent the set of values of this random experiment, of this random variable, which we could represent as x of omega equal to the discrete set 0, 1, 2. Now remember, this is a discrete, a random variable, discrete because the set of values it can take is a discrete set. It has specific values. It's not a continuous interval. So over here, since 0, 1, 2 are the possible values that this random variable can take, basically we could end up having x equal to 0, x equal to 1, or x equal to 2. Now these are called elementary events of the random variable x, and these are the events that you end up determining the probability to. For example, if we consider x equals to 0, x equal to 0 would represent the event that says no head is obtained. which if you look down here, the probability of having x equals to 0 is in fact 0.25 or 1 out of 4, because out of the possible outcomes of the sample space, only the outcome with 2 tails can give you no heads. So that would be 1 out of 4. Similarly, x equal to 1 represents the event exactly 1 head is obtained. So again, if we look at the sample space omega of this random experiment, we'd notice we have 2 outcomes that could give me exactly 1 head, and that's 2 outcomes out of 4. So that's 2 out of 4, which is 0.5. And then finally, we have x equals to 2, which is the event 2 heads are obtained, and the probability of x equals to 2 is again 1 over 4 or 0.25. Since out of omega, the sample space, we only have one outcome that could give you 2 heads, and that's 1 outcome out of 4 possible outcomes. So if you look at this table here, this is called the probability law or the probability distribution of the random variable x, which the first row would actually be the possible values that the random variable x can take. So over here we have possible values that x can take, x as capital X, the random variable. And then this is the probability of x equals to xi. This is an I. Okay, so this is the probability of occurrence of x equals to xi. As you can see, this is xi equals to 0, so the probability of x equals to 0 is 0.25 as determined here. The probability of x equals to 1 is 0.5, and the probability of x equals to 2 is 0.25. Since x equals to 0 and x equals to 1 and x equals to 2, these 3 events should basically form a partition of the universe. So their probabilities should end up giving you a total probability of 1, since these events are in fact a partition of the universe. They do not intersect 2 by 2. Their union is the whole sample space, and in addition, they do not intersect 2 by 2. I've already mentioned that, and each of them is not empty. So for that reason, being a partition of the universe, you have to end up with the sum of their probabilities equals to 1. Now over here, if we have a random variable, and this being the probability distribution table, now as I've already mentioned, the random variable could be seen as a statistical variable, but that statistical variable, instead of studying the number of occurrence or the frequency of certain values, would actually be studying the probability of occurrence of their corresponding events. So, and similarly to any statistical variable, we can determine a mean, a variance, a standard deviation, and a mode. So over here, if we look at the mean, which is called the expected value of the random experiment, which is denoted by E of x. So the expected value of the random experiment is the average it's the average, in fact, of the variable, so which is determined by taking the value multiplied by its probability plus the second value multiplied by its probability plus the third value multiplied by its probability, etc. So the expected value is in fact determined by adding the product of the values of the random variable with their corresponding probabilities. Okay, so in fact, E of x, the expected variable, is considered to be a weighted average. It is a weighted average because each value of the random variable is weighted by its corresponding probability. So the value you end up with for the expected value would actually be considered as the value that you would be expecting as an outcome. Now, for the variance, you'd notice that the formula is similar to the one you use in statistics for statistical variables. So the variance of x would in fact be the probability multiplying the value of the random variable minus the average, all squared, or you could be using the other formula we have or we use for determining a variance, which is the average of the square of the values minus the square of the average of the random variable. So over here for the first one, this is the sum of xi squared times the corresponding probability of each value, minus, of course, the square of the expectation that you determined, which is the sum of xi times its corresponding probability all squared. So the variance could be determined using either of these formulas. And of course, as we know, the standard deviation is in fact the square root of the variance. Now, when it comes to determining the mode of a random variable, similar to statistical variables where modes are the values of the variable with the highest frequency, now over here, the mode of a random variable would be represented by the value of the random variable that has a maximum probability, which is the value that is most likely to occur. So that is the value that is most likely to occur. Now, if your variable is normally distributed, usually the mode and the mean are pretty much closer to each other than what if the variable is not normally distributed. Now, if we look at this example, we have a pair of fair dice that are tossed. So over here, fair dice, we know that each die has 1 to 6 as possible outcomes. So for each die, we have 1 to 6 as a possible outcome. So this is die 1. As for die 2, we also have 1 to 6. So when you toss both of them, the sample space would consist of the ordered pairs that are formed by the outcome of the first one and the outcome of the second one. So over here we have 36 possible outcomes or possible ordered pairs formed by 1 with 1, 1 with 2, 1 with 3, all the way to 1 with 6. Then 2 with 1, 2 with 2, 2 with 3, all the way to 2 with 6. So this is why we do have 36 as 6 times 6 possible outcomes, because we can look at it here as we have 6 possibilities for each die, and that's with repetition, so this is 6 squared. So over here we introduce the random variable that associates for each outcome its minimum value. I remind you that there is no one random variable specific to each random experiment. To each random experiment we can define many random variables. So the study really depends on how you define the random variable you're introducing to your random experiment. So over here we have x to be the random variable that associates for each outcome its minimum value for each outcome out of omega. So over here, for each outcome is represented by an ordered pair, where the first digit would be the outcome from the first die, and the second digit would be the outcome from the second die. So x, our random variable, is defined by the minimum of these two values. So over here, and of course, whenever the two numbers are equal, we consider that the minimum is equal to them. And for example, here, the outcome 1, 1, there is no smaller value, so we'd consider the minimum to be 1. So in that case, the possible values that the random variable can take are 1 to 6, because if we have 1 in any ordered pair, that would be the minimum value. And if we have, for example, 2 with values that are at least 2, then 2 would be the minimum value, etc. And then 6, 6, that would have a minimum equals to 6. That's the only outcome that would give you a minimum equals to 6. But however, it is part of the possible values of our random experiment. So x of omega here would be 1, 2, 6. So if we were to set up the table that represents the probability distribution of this random experiment. Now over here, xi, as usual, the first row would actually contain the possible values of the random experiment, which in this case are 1 to 6. And the second row would in fact represent or include the probability of x taking each of these values. So if we look at the first one, this is the probability of x equals to 1. Now, what is the probability of x equals to 1? In order to determine this probability, we need to count how many ordered pairs out of inside omega actually include 1 as at least one of the two outcomes from die 1 or die 2. So as we've said already, 1 would be the minimum of the two outcomes if the ordered pair contains at least a 1. So in order to count how many we have here, don't forget that we'd have 1, 1, of course, with a minimum equals to 1. Then we have the ordered pairs that start with 1, which are 1 with 2, 1 with 3, 1 with 4, 1 with 5, and 1 with 6. However, over here the order matters. It means that 2, 1 is another outcome other than 1, 2. So over here we'd also have 2, 1, 3, 1, 4, 1, 5, 1, and 6, 1 as ordered pairs that have a minimum of 1. So if we count them, these would be 11 out of the 36 we have in omega. So the probability of x equals to 1 would be 11 out of 36. Now, to have a minimum of 2, similarly, you just count the outcomes with minimum equals to 2 the same way you count it for 1. For example, if you look at them here, of course we'd have 2, 2, which is one possibility, 2, 2, and then 2, 1 is no longer counted because 2, 1 has a minimum of 1, and 2, 2 we already have it here, so it's 2, 3 all the way to 2, 6, and similarly we'd have 3, 2 all the way to 6, 2. So these would actually be 9 out of 36 if you were to actually count them. Okay? And you would count the rest exactly the same way. So probability here of x equals to 3. So to find the probability of x equals to 3, you'd have to in fact count the ordered pairs that would give you a smaller value equals to 3. For example, you'd have 3, 3. And then for the rest of them, the ones that are in fact that are found twice with the order flipped, that'd be 3 to 4 all the way to 3 with 6, because 3 with 2 would have a minimum of 2, and then we'd have 4 to 3 all the way to 6 to 3. These are 3 each, so that's a 6 plus 1, so that's a 7. And then you'd count all of them, and then you'd basically determine the probability of each of the rest similarly. Now over here, to confirm you have calculated the probabilities correctly, all you have to do is just add these probabilities and you should have a sum of 1. For example, 11 plus 9, that's 20, 27, 32, 35, and 36. And 36 out of 36 is 1. So that way you would be sure that you had the correct probabilities. Now, in many cases, students do ask me if they could just determine, for example, here the first 5, and instead of calculating the 6th one, if they could do 1 minus the rest of them, the sum of the rest of them. Well, what I do say every time is that theoretically that is not wrong. You can do that because the sum of the probabilities is 1. So the last one should be 1 minus the rest of them. However, I'd rather you don't do it that way, because this is a way for you to determine if you had been calculating your probabilities correctly. So over here, by just finding all of them and then add them to check if they add up to 1, that way you would actually confirm if your work had been correct or not. Because what are the odds of you having wrong probabilities and the wrong probabilities adding to 1? Now the odds are really negligible here. So for that reason, I'd rather you use the sum equals to 1 as a way for you to check if you had been working out the probabilities correctly, rather than using the sum equals to 1 to find the probability of the last event. Because in that case, if your probabilities are wrong, by doing that, you would in fact be ending up with the sum equals to 1 with wrong probabilities. You would not be able to tell your work is not correct. Now, if we look at this example, we have 4 light bulbs that are chosen from a box containing 18, which we know that 4 are defective. We have here a box of 18, which we know that 4 are defective and the rest 14 are not defective. So we need to find the expected number of defective items among the bulbs chosen. Now over here, according to this, that we are randomly choosing 4 bulbs out of this box. We already know that among these 18 light bulbs, 14 are not defective while 4 are defective. And then my random experiment is consisting of just choosing randomly 4 bulbs out of this box. And I need to find the expected number of defective items. Whenever we speak of an expected number, that is in fact the expectation of the random variable, or the average of the random variable that you have defined on your random experiment. However, as you can see here, we do not have a random experiment defined. We'd have to define a convenient one. So usually how you define your random variable really depends on your question. What are they really asking you to find the expected number to? They're asking you to find the expected number of the defective items among the ones that you are choosing randomly. So over here, the random variable, the proper or the convenient random variable that you need to define is in fact the number of defective items among the 4 items chosen. So we start by defining the random variable as follows. Let x be the number of defective light bulbs among the 4 chosen. Okay, so The first step is defining your variable. The second step is defining your set of possible values for the random variables. So we start by defining x of omega. So x of omega, the number of defective light bulbs among the 4 chosen. What are the possible values that you can take? For example, out of the 4 light bulbs that you're choosing, how many possible values can you end up having? So among the 4 that you have chosen, you could have 0 defective, 1 defective, 2 defective, 3 defective, or 4 defective, because in total we already have 4. We know for sure that we have 4 in that box. So among the 4 that you're randomly choosing, you could have 0 defective to 4 defective. So over here, that's 0, 1, 2, 3, and 4. So x of omega, which is the number of possible values that the random variable can take, are in fact 0 to 4. So in order to determine the expected number, we need to start by setting up the probability distribution of this random experiment. So over here, we need my probability distribution, which consists of xi, and probability of x equals to xi. So we have here 0, 1, 2, 3, 4, and we do have the total. The total which we know that should end up being equals to 1, and that is, as I've already mentioned, our way to determine if we have calculated the probabilities correctly. So over here, this would in fact be the probability of x equals to 0. This is the probability of x equals to 1. Here should go the probability of x equals to 2. This is the probability of x equals to 3, and this is the probability of x equals to 4. So yeah, let's determine each of these probabilities. So before you determine the probability of any event in a probability problem, the first thing you need to do is determine the number of possible outcomes in this random experiment, which is the cardinal of the sample space. So what is cardinal of omega here? So I go back to my experiment. I have 18 light bulbs in the box. Over here, to determine cardinal of omega, I don't care if they were defective or not defective. So over here, I have a total of 18 objects, out of which I want to choose 4 randomly. Now over here, is this experiment done with or without repetition? Of course it is done without repetition, because I do not care about the order out of which I'm choosing the light bulbs. What I care about is the number of defective items I ended up with eventually. So over here, how many 4 bulbs can I choose out of 18 without order? So that's a combination of 4 out of 18. So a combination of 4 out of 18 would actually be 18 C4, which is 3060. So there are 3060 ways I could be choosing these light bulbs, these groups of 4 light bulbs. Now let's just start with the probability of x equals to 1. Now the probability, let's just start with 0 first, probability of x equals to 0. So we know that we have a total of 3060. So over here, the probability of x equals to 0. Now x equals to 0 is the event that corresponds to no defective light bulb chosen. So over here, no defective bulb chosen. So what does it mean that no defective bulb is chosen? It means that the 4 bulbs you have chosen were chosen out of the 14 bulbs that are not defective. So it means here the cardinal of this event would be combination of 4 out of 14. So it's 14 C4, which is 1001. So that's 1001 over 3060. So that's 1001 over 3060. Now, similarly, the probability of x equals to 1 would in fact be the event corresponding to, would be the probability of the event corresponding to choosing 1 defective and 3 not defective. So out of these 4 that are defective, I'm choosing 1, and out of these 14 that are not defective, I'm choosing 3. So this is a combination of 1 out of 4 times combination of 3 out of 14. So this is 3 out of 14 over the total 3060. So that would in fact be combination of that's 14C3 on the calculator, and that's a times 4 because combination of 1 out of 4 is 4. So that's 1456. So that would be 1456 over 3060. Now, similarly, the probability of x equals to 2 would in fact be choosing 2 bulbs that are defective. So over here, I'm choosing 2 out of these 4 and 2 out of these 14. So that's C2 out of 4 times C14, 2 out of 14 divided by 3060. So that would in fact be C2 out of 4 times C2 out of 14, which is 556. So that would be 546 over 3060. And similarly, we determine the remaining 2 probabilities. Probability of x equals to 3, that's the probability corresponding to choosing 3 that are defective. So this is 3 out of these 4 and 1 out of these 14. So that would be the combination of 3 out of 4, which is 4 times the combination of 1 out of 14, which is 14. So that would be 4 times 14, which is a 56. And then the probability of x equals to 4, it means that I have chosen my 4 bulbs out of the 4 that are defective. So that's C4 out of 4, which is 1. So that's 1 out of 3060. And you can always make sure that the numerators add up to 1. So I was not simplifying fractions here. So the denominators would be equal for all of them. It would be easier to check the final sum. So 1456, 546, and 56 plus 1. So we do have 3060. It means that we have calculated our probabilities correctly. So regarding the expectation, so we need to determine the expected number of defective items. So the expectation would be the product of each value of the random variable with its probability. So 0 times 1000, 1 over 3060, that's a 0. 1 times, so that's 1456 over 3060, plus 2 times 546 over 3060, plus 3 times 56 over 3060, plus 4 out of 3060, which gives, let me just separate here, which gives, if we were to calculate or to add the numerators, 1456 plus 2 times 546, yes, plus 3 times 56 plus 4, and that is of course divided by 3060, which gives 0.85 to 2 decimal places. Now, what does that mean? It means that whenever you perform this random experiment, whenever you have that given box and you choose 4, you are expected to have 1 defective items among the 4. So you're expected to have, in fact, at most 1, because the expectation is even smaller than 1. So you're expected to have almost 1 defective items among the 4 chosen. So if we were to just look at this last example before we wrap this up. Now we have a player that tosses a fair die. If he gets an even number, he wins that number of points. If an odd number appears, he loses that number of points. So is the game favorable? Now, whenever it comes to these games, when are games considered favorable, not favorable, or fair? In fact, over here, if the game is favorable when you are expected to win more than losing. If the game is fair, it means you are equally likely to win as you are to lose. Okay? And in fact, over here, in order to determine if the game is favorable, we need to determine if he is more likely to win than to lose. And how would we do that? First of all, we need to determine or define a convenient random variable to this exercise, and then we need to find its expected value. Now over here, since this experiment consists of losing and winning, if his expected value is positive, it means that he is more likely to win than to lose. If the expected value is 0, it means that he is equally likely to win than to lose, then the game would be fair. However, if his expected value is negative, it means that he is more likely to lose than to win. So the random variable that we need to be defining here should be representing the amount gained or lost by the player in order to determine or end up with a positive or a negative or a 0 expectation. Because don't forget that E of x, the expectation, is the expected outcome of this random variable. So we need to know if he is expected to end up with a positive outcome, or is he expected to end up with a negative outcome or a 0 outcome. If his expected outcome is positive, it means he's more likely to win in this game. If his expected number is negative, it means that he's more likely to lose. And if his expected outcome is 0, it means that the game is fair. He is likely to win the same as he is likely to lose. So over here we need to start by defining the random variable x that would represent the amount gained or lost by the player. So once we define the random variable, we need to determine x of omega, which is the set of possible outcomes. So when you roll a fair die, now over here you could end up with 1 to 6 as a value on the top number. So over here it says if he gets an even number, he wins that point. So these are the even numbers. So he could, if he rolls a 2, he would have a plus 2. If he rolls a 4, he's expected to have a plus 4. And if he rolls a 6, he's expected to have a plus 6. However, if an odd number appears, he loses that number of points, which means that if he rolled a 1, he's expected to lose a 1 point. If he rolled a 3, he's expected to lose 3 points. And if he rolled a 5, he's expected to, he would in fact, not expected, he would in fact lose 5 points. So these are the possible values that this random variable can take, which x is in fact representing the amount gained or lost, or you can say amount of points, since this could be confused, as the word amount could be confused with money. So over here it's the amount of points gained or lost. So they would in fact be -5, -3, -1, then 2, 4, and 6. Okay? So let's just set up the probability distribution. So over here we have xi, and we have the probability of x equals to xi. So these are the values of my random variable, -5, -3, -1, +2, +4, and +6. And we have, of course, the total that we know should end up being equals to 1. So over here, what is the probability of each? Now over here, the probability of x equals to -5, the probability of x equals to -5, that's in fact the probability of rolling a 5. We know that rolling each of these outcomes in a fair die, they are actually equiprobable. Each has a probability of occurrence of 1 out of 6. So since over here 5 has a probability of occurring of 1 out of 6, then the probability of losing -5, that the probability of losing 5 points is in fact 1 out of 6. It has the same probability of rolling a 5. So similarly for the rest of them. So over here, since each outcome corresponds to one face of the fair die, it means that each outcome has a probability of 1 out of 6 of occurring. So over here, in order to determine if the game is favorable, we need to actually determine the expected outcome. So we need to find the expectation of this random variable. So over here, E of x would actually be -5 out of 6 minus 3 out of 6 minus 1 out of 6 plus 2 out of 6 plus 4 out of 6 plus 6 out of 6. Now over here you notice I'm not simplifying my fractions because I want to be able to just add them up easily. So over here this is -8, -9, then -7, -3, and 6, that's a 3. So over here we have 3 out of 6 as a sum here, which is a half. So the expected value is positive. So he is expected to end up with a positive amount of points. So he is in fact expected to win more than losing. So the player, we just end up saying that the player is more likely to win. So the player is more likely to win than to lose. Okay?